Go back and check. Yeah.
Okay, so let's get started. So today we'll continue our discussion from last time. We started talking about concurrency and scheduling. Okay, so last class was largely concurrency. Today we'll switch gears, talk more about scheduling, and then we'll continue that next time as well. Okay, so today's class is going to be on distributed and cluster scheduling. And by the way, because we have now covered the server concurrency models, all the multi-threaded models we talked about last time, we have a lablet for it, which I'm going to hand out today. I think the skeleton code in that lablet will be quite useful for the lab that we have already handed out, right? Because the lab requires you to use RPCs or socket communication. We covered that, and that also was part of lablet 1. But it also requires you to write a simple server application. Okay? And that was something we covered last time. So take a look at the skeleton code in both of those lablets. Feel free to use it any way you want for doing your lab work. Okay? And just keep in mind, the lablets are really tutorials. So we are not really grading you for correctness. So long as you just did it, you get full points for it. Right? So they're lightly graded. Lab is where you should be spending your effort on, because that's the thing that actually counts towards the grade. Okay? Because lablets, really, we are giving you the code and just saying try it. That's not really going to require you to do a lot of work. Okay? So keep all of that in mind. And as usual, if you have questions, come ask us. We're happy to help. We have addressed several of the issues that have been brought up on Piazza with regards to the Docker container. There are some minor things left. We will address those shortly, and hopefully everyone can then use the container as the Docker container as your development environment. Okay? All right. Yes. Camera does not show. All right. Okay. Looks like the video is not going to the thing. Okay. So in any case, let's start with the part 1, which is multiprocessor scheduling. Okay? So we are switching gears from thread scheduling and thinking about how threads are scheduled and so on, to now, because this is a distributed systems class, we are going to think about how are processes scheduled when your machines with lots of processors, or how are processes scheduled when you have systems with lots of machines, right? So we are now going to go beyond a single machine. First, we are going to talk about multiple processors on still a single machine, but then we are going to look across machines and how do you do scheduling. Okay? So part 1 is multiprocessor scheduling. Okay? So here is the picture that you want to keep in mind of what is a multiprocessor. Okay? So what you want to think about is a machine that has many processors or cores. We'll use the term processor or core interchangeably here, although they are not exactly the same thing. For the purposes of this class, doesn't matter. Okay? So these things that are in purple circles are processors. Okay? And then, or the purple circles are processors. The yellow boxes are memory of different types. Okay? So there is the level 1 cache that's attached to a processor. That's the small yellow box that's literally shown inside a circle. Okay? So those are actually dedicated to a processor. Then you have a level 2 cache, okay, that may be dedicated, that's still dedicated. And then you have memory that's shared across processors. Okay? So any processor can access data from any memory, but it has to only look at its caches to when it's trying to access data. Okay? We'll see why some of these things matter, but this is a hardware picture. So if you have an undergrad course in computer architecture, you would have learned something about processors and level 1 caches and level 2 caches, which is the kind of background you need for OS or hardware, systems classes. But even if you don't have that background, doesn't really matter. All you need to realize here is we have a set of processors on the machine. Okay, they have fast memory, which are called caches. They are arranged in hierarchy. So level 1 cache is smaller and faster than a level 2 cache. And both of those caches are smaller and faster than memory itself. which is actually shared across all of those processors. Okay, and we'll see what, and some caches may also be shared. Here we have not showed any caches that are shared. They're all dedicated. Okay. Now, with that picture in mind, let's start thinking about scheduling processes or threads onto these processors. Okay. So here are two ways you can build your scheduler. Okay. The first approach is all processes or threads, applications, they are waiting in a queue, a single queue. Okay. And then the processors themselves, whenever they become idle, whenever the time quantum on that processor expires, the OS code on that processor, OS kernel on that processor is going to look into the queue, extract a process or a thread, execute it. Okay? So every time a quantum on a processor expires, because remember I said last time, all CPU scheduling uses time slicing or quantum. You allocate one quantum, which is a unit of time of the resource, to each thread at a time. So whenever your, let's say, quantum is 10 milliseconds, every 10 milliseconds, you basically, the quantum expires, the scheduler tries to pick another task to run on that process. Okay, and you might do round robin and things of that sort. Okay, so this uses a single queue across processors. Another approach is you can have more than one queue. In the limit, each processor has its own queue. Okay, and there are tasks or threads in that queue. So when that processor's time slice expires, it only looks at its local queue. Okay? Here's a picture where we have something in between where each queue is shared by two processors. Okay? And then that one, all processors share a single queue. Okay? So you can design your scheduler where you can either have one shared queue or more than one queue which might be dedicated. Okay? So then the question is, what are some pros and cons of using these approaches, okay, for performing our scheduling? So if you have a centralized queue, okay, so remember that queue is essentially a shared data structure. Okay? It's just a list of threads that are waiting to be scheduled. Okay? So this queue is a shared data structure. So if you have a centralized queue, it's going to quickly become a bottleneck. Is it clear why it will become a bottleneck? Okay? There will be lots of processes queued there. That's true. But that is not going to make it a bottleneck by itself. The length of the queue is not the problem. Yes.
There's a certain amount of time that it takes that has to be done by one things, everything
Okay.
parallel.
All right. So the last thing you said is the most important thing. Okay. The queue is a shared data structure. It's a shared queue. Okay. If there are multiple processors trying to access it, you have to protect it with a lock. Okay. Just as, because it's a shared data structure, you can't have two processors go and try to take things off at the same time. That's going to lead to corruption. So if you're protected it with a lock, okay, let's say one processor core is trying to extract something from a queue, another processor becomes idle, it cannot do anything until the first processor is done. So until that time, that processor will be idle. So it cannot even get a task of that queue to run. Okay? So this is basically a synchronization problem. As the number of processors grow, okay, you will essentially start contending for the queue, and you may be blocked waiting for a lock on the queue, and then the processor is just sitting there idling, waiting to just take a turn to get something off the queue. Okay? So that's the problem. Okay? Of course, the number of threads can grow, but that by itself is not going to be the main issue here. Okay? So that's a disadvantage. But the good part is that since it's one queue, any processor can pull tasks on that queue. So even if there are lots of tasks queued up, okay, you can essentially assign them to any idle processor and make use of all of the processors. Okay, there's a question somewhere here. Yes, you had a question. You did not understand the lock part. Okay, so assume that each of these processors. First of all, you need to know what a lock is and why you need to use it. Okay, in any system where you have concurrency, whether you have multiple processes or multiple threads trying to access a data structure, you need to use a lock to protect that data structure. You cannot have data structure be written to by more than one element at once. Okay? It's a basic principle of synchronization and threads and concurrency. Okay? Here, you will have a kernel thread running on each of these processors trying to schedule the next task. They're all essentially trying to access the shared data structure. So all of those kernel threads must use a lock to pull things off the queue, right? So that is why you need a lock. Okay, all right. So queue can be a bottleneck, but it basically ensures that all processors are going to be utilized if there are many tasks queued up there. Okay, we'll come back to why the cache affinity can be a problem. But let's talk about distributed queues. Okay, what might be some advantages and disadvantages? So so rather than this picture, assume that there's one queue per core. Okay, this shows one queue for every 2 cores. There's one queue dedicated to a core. Okay, so in this case, there is no contention, because there's no other processor is going to try to pull threads of that queue, because there's one processor that's assigned to each, one queue assigned to each processor. Okay, so there's no contention, very little contention in this case. So that bottleneck problem is gone. Okay, as soon as the time slice expires, you can go to the queue, take the lock, extract the next task, run it. Okay, so this problem is eliminated. Okay, but now you have a different problem, which is you have more than one queue. Okay, if the number of tasks in those queues is not the same, okay, the queues are going to be imbalanced. Okay, some queues might have more threads, some queues might have less threads. So some processors are more loaded than other processors. So the load on processors will be uneven if the number of tasks assigned to those queues keeps changing. Okay, so this is going to cause an imbalance in the system, where some threads make faster progress because they are in shorter queues, so they can run more often. If you're doing round robin, you will get more quantum, and some will get less. Okay? So this will require you to then periodically go and rebalance the queue if it becomes imbalanced. Okay? So the queue can get imbalanced, okay, but you have to do extra steps of rebalancing the queue, which means more tasks from one queue to the other, so that the queues are of the same size. Okay. Now the important part, the why I showed you the picture of what a processor looks like and what the caches look like is, in any processor system, okay, so the processor makes heavy use of its cache for efficiency reasons. Okay, because going to RAM to fetch data or code is always slow. Okay, but once that data is cached in your L1 and L2 cache, you can access it maybe an order of magnitude faster or more. Okay, so this speeds up the execution of the task. Okay, now when you have one queue per processor, okay, the same task will execute on that processor over and over again across time quantum. Okay, so let's say the task executes, the time quantum expires, it goes back to the queue. Okay, after a while, it will execute again. Okay, and it will execute on the same processor. Okay, that is important because whatever data it had brought into the cache previously will still likely be in the cache, and it can make use of it again. Okay, that's called cache affinity. Okay, now in that other scenario, you will see what happens if let's say task A runs on processor 1, its time slice expires, it goes back to the end of the queue. Okay, next time it might go get assigned to some other processor. Okay, now processors do not share the caches. That's what I just showed you here. Okay, so if it ran here, the data is in this cache. Next time, if that same task runs on some other processor, that cache has none of its data or code. So it will start with the cold cache. It will get a set of cache misses. Its performance will slow down quite dramatically, as it turns out. Okay, so you will start seeing cache misses, and that basically causes the performance to suffer. So you have poor cache affinity. Okay, this is actually the single biggest disadvantage of that shared queue. Bottleneck is not the big problem. Okay, even if you solve that problem, the performance hit that the processes take because they keep changing processors is actually a bigger problem. Okay, and that's something you have to take care of. And and the distributed queue, of course, gives you that, okay, because you are going to have cache affinity, you are going to run on the same processor over and over. Any questions on this? Okay, so that is very quick overview of multiprocessor scheduling, but there are many. I did not talk about the policy. I was just talking about some hardware details and whether the policy that you use is going to be implemented using a single queue, multiple queue, and so on. It doesn't tell you how actually tasks are scheduled onto processors. So I'm going to talk about one specific policy, which is called gang scheduling. Okay? Gang scheduling algorithms are used for parallel application. Okay? This is an application with many threads or many processes that are running on the same machine. We haven't yet gone across machines. We have not started talking about distributed scheduling. We are talking about more than one processor or core on the same machine. Okay? So you have a parallel application. It has many threads or many processes. Okay? What is the best way to schedule this application? Okay, the way you do this is essentially you schedule them as a group. Okay? You can take all the, let's say there are n cores. Okay? You can take n threads of that application. You schedule them all at once on n cores. Okay? So this kind of you're coordinating what is running on all the cores. That actually gives you better performance than if each core independently decides what runs on that core. Okay? The reason coordination and trying to run them as a group or a gang, which is why it's called a gang scheduler, is because it actually reduces blocking overheads. Because when these threads communicate, okay, let's say thread 1 sends a message to thread 2. If thread 2 is not executing, then that you have to wait for that thread to actually run before that message can even be processed. But if they're all actually executing at the same time, when you send these messages back and forth, they can be processed immediately. Okay? Because the thread is already executing or the process already executed. So it reduces blocking overheads, okay, when you have a message passing or IPC. Okay? So it's a very common approach used for parallel applications. Okay? So that's something you want to keep in mind. But there are lots of issues you have to deal with when you try to implement gang scheduling algorithms. One of them is what happens if one of the thread of that gang blocks. You have n of them running, one of them does IO. Okay? As soon as you do IO, that thread is going to block. Okay? But the others are still executing. Okay? What should be done in this case? Should they be let continue execution, or should you say one thread blocks? Let's just assume that the quantum has ended and just have all of the threads go back to their queues and schedule some other gang. So either of those two approaches work. So you can either preempt the entire application, that's called co-scheduling. If any thread blocks because it's trying to get a lock or it's trying to do IO, you will essentially deschedule all the other n-1 threads that are running on other processors. Okay? So that's preemption. Okay, the other thing is you said, no, maybe you don't do that. You essentially ensure that the others can continue to run until the quantum expires. In this case, if there's any messages sent to threads that are blocked, that will still cause performance issues. Okay? So there are both flavors of gang schedulers that are out there, but just something you want to keep in mind as one example of multiprocessor scheduling, where you are taking advantage of multiple cores and trying to schedule different components of an application. There could be threads or processes in a coordinated fashion, all n at once onto n cores. Is this clear? Okay. So that's all. Yes. What the question is, what is the commonality between the n threads? It's a parallel application. So typically in a parallel application, the threads are trying to perform the same task, but it's parallelized, right? So that's the general assumption. Yeah. So question is, if I said you preempt that entire application, schedule another gang, is it a different application? In this case, it will be a different application. Right? So that's the assumption. Okay. So we will move on. We'll now switch gears and actually get to the real topic we wanted to discuss, which is distributed scheduling. This is a distributed systems class. So thread scheduling, multiprocessor scheduling is still scheduling for one machine. Okay? But our goal is really to think across machines. So now we finally got there. So let's start thinking about distributed scheduling. Distributed scheduling comes in many different flavors. So I'm going to first give you a really early version of distributed scheduling, okay? Which was scheduling tasks on a set of workstations. And then we'll get to cluster scheduling, which is distributed scheduling as it exists today. Okay? But let's first start with how it arose maybe in 30, 40 years ago. Yeah? So to understand this flavor of distributed scheduling, you need to have some background in mind. Okay? So distributed scheduling actually arose when PCs and workstations became common. Okay? So we'll assume that every user has a machine on their desk. Okay? This is the environment you want to keep in mind. So you have, let's say you are in an organization, it's either a company, or maybe it's an academic department like the one we have here. Users, okay, have, this is pre-laptops, right? So we'll assume you actually had a desktop that is sitting on your desk. Okay. Now, we will also assume that users are not using their machine at all times. Okay. Maybe you have gone to class, your machine is idle in your office, okay? Or maybe you went to lunch and your machine is just sitting idle on your desk. Okay. So you will have some machines that are being used, other machines that are not. Okay. So the question is, can you can you harness idle cycles on machines that are not in use and make better use of all the machines in the network, right? In particular, let's say some machines in the network become heavily loaded because that the users of those machines just start running many applications on them. Okay. So the load on those machines goes up. Okay. But there are some other machines in the network, some other users' machine just sitting there idle, not doing anything. Okay. Then the question is, can you take some work that's being done on the overloaded machine and move those tasks to an idle machine and spread the load around? Okay. That is what we'll call distributed scheduling. Okay. So the idea is that we will decide what tasks run on what machines in the network so that we can take advantage of all the machines in the network and specifically take advantage of idle machines that are not doing anything. Okay. If they're not doing anything, might as well use them to perform some computation. Okay. That's the basic idea. Okay. So the picture, and I'll show you approaches, the picture you want to keep in mind is the user submits a job or starts an application on a local machine. That's their machine. Okay. The OS has to then decide one of two things. When the user starts a new job or an application, should that run locally? That's the normal case. Right? You start a browser or whatever, it runs on your machine. Right? So that by default, it will run it on the local machine itself. But if the machine is overloaded and there are some idle machines in the network, the OS can actually remotely run this job. It can say, why run it on this machine? Let's start it on this other machine that's idle and run it there and provide the results to the user. Okay? So that's the decision an OS has to make. Should you schedule a job locally or should you schedule it remotely? Is that clear? Okay. Now we'll try to analyze this idea in a lot more detail to see how this is done, when it is beneficial, and so on. So the first thing we'll ask is, when does this type of approach where an OS decides to schedule a job somewhere else, when is it beneficial at all? Okay. And we'll do a very simple analysis here. Okay. There's no math here, but you at least have to understand what probability means, okay, probability distribution. So to understand distributed scheduling, we have to analyze this question. Okay. The question is, what is the probability that there is at least one system or one machine idle, okay, and there's one job that's waiting, which means that it needs some machine to run. Okay. What's the probability that both of those things are true at the same time? Okay. That there's an idle machine in the network and there is a waiting job in the network. Is the question clear? What are we trying to ask? Okay. So now let's try to analyze this question. Okay. So we are not going to do a math analysis. We could, but I'm going to give you a more intuitive analysis of that problem. Okay. Let's assume that the system is heavily utilized. System means all the machines in the network are heavily utilized. Okay. So we are now considering a scenario where the networks, the machines in the network are heavily utilized. Okay. And the first question we'll ask is, if the system is heavily utilized, what is the probability that there's an idle machine in the network? Low. All machines are by default utilized, so the chances of finding an idle machine is low. Okay. And we'll also ask, in that scenario, what's the probability that there's a job waiting to run? Okay, because it's heavily utilized, okay, there's a good chance that the user starts another job and it needs some machine to run because that machine is overloaded. Okay, is that clear? So then you say, what's the combination of both of those? So that's an AND operation. So because there's no machine that's idle, okay, the probability that both of those things are true is actually low. So you will not get much benefit of distributed scheduling. Okay, because if the OS scheduler says, okay, here's a job that needs to be offloaded to some other machine because the local machine is idle. Okay? It will try to go find an idle machine. It will not find any, typically, because the probability of finding a machine is low. So a distributed scheduler is not going to give you any benefit in this case. Okay? Because there are lots of jobs that are willing to run on some other machines because their local machines are idle. But there are no idle machines to be found. So even if you implement distributed scheduling, the OS will say, I cannot find an idle machine. So it will continue to run the job locally because there's nowhere else to run it. Is that clear? So in heavily utilized scenario, okay, there is little benefit to using distributed scheduling. Okay? Because the probability that both of those things are true at the same time, actually, and it becomes low. We'll take the other case. We'll assume now a lightly loaded system. Okay. So the question is, what is the probability of having an idle machine in the network when the load is low in the system? Okay. It's high because machines are lightly loaded or not used, so there are many idle machines in the network. Okay. And you say, what's the probability that there's a waiting job in the network? Okay. It's low because there is not much happening. So as soon as you start a job, it can run locally. It doesn't have to wait. Okay. Then you say, what's now the benefit of distributed scheduling? Okay. So in this case, the OS has no need to find another machine to run. There are many machines that are idle, but there's no job that you will find that needs to run on them because it can run locally, which is always the best choice, right? Because your load is low, so you just run it locally. There's no need to go find another machine. Okay. So in this case, there is no benefit to distributed scheduling either, because now you have the opposite case where there are plenty of resources, idle resources, but no jobs to run them. Okay. In the previous case, there are lots of jobs, but no idle resources that were to be found. Okay. So in both of these two cases, distributed scheduling of the flavor I just explained to you has little benefit. Okay. Does that mean this is not useful? Any thoughts? Okay, there is something in between low and high, right? You can have something moderately utilized system. So the only time actually this approach gives you benefit is when your system is moderately utilized, neither lightly utilized nor heavily utilized. Okay? And the probability distribution of that thing is actually shown here. This is under different scenarios. You will see that the probability both of those events are true at the same time is low, and the load is utilization is the x-axis, probability is the y-axis. So here it's low, so showing no benefit. Here is low, saying there's no benefit. But in the middle, it says that you will actually have benefit. Okay? That you will have an idle system and there is a job to run. So distributed scheduling actually makes sense. Okay? So this basically tells you there are limitations, even though this might all sound good. Let's try to use resources on all of the machines. There are many scenarios that you will not find much use when you implement these types of approaches. But there are some other scenarios where you will find some benefits, and those are the ones where system is moderately utilized. Okay? That's basically, if you do the actual math analysis, it will tell you the same thing. But I gave you an intuitive explanation, okay, of when these types of approaches are useful. Is that clear? Okay. Now, there are many details which I glossed over, but we really don't need to go into this, which is what does performance mean? Is a mean response time? Okay. How do you measure load? When I say it's idle, you can say, okay, it could be CPU utilization, it could be the queue length. There are many metrics. It doesn't really matter how you define them. The abstract definition of load and whether there is a job waiting, regardless of what you pick, you will get the same answer at the end of the day. Okay. So we'll just go with that understanding and now talk about actual distributed schedulers. Okay. How do you build one? Okay. Any of these distributed schedulers for this network of workstation approach, okay, has 4 components. Okay. There's something called a transfer policy, which says when should you transfer a process to another machine. Okay. That's called a transfer policy. When should the OS decide this job should not run locally, it should actually, you should try to find another machine to run it. Okay. Transfer policy. Selection policy says which process to transfer. The machine is overloaded, you have to send some process to some other machine, which one should you transfer of all the ones that are running on the local machine? That's called a selection policy. Location policy says where to transfer this job, which machine. If there's an idle one, which idle machine, or how to find that idle machine. That's called the location policy. Information policy says what information should the OS keep to make all of those decisions. Saying when to transfer the job, which job to transfer, where to transfer the job. So there's 3 questions. So there's when, which, and where. So we'll see some example policies that tell us what to do for each of those cases. The first one is called sender initiated policy. So sender initiated, as the name suggests, in the sender initiated policy, the machine that's making all this decision is the sender. It's the machine that's overloaded, that's trying to offload work. So all of the work of where to send it is all done by the machine. That's the one that's sending the job to some other machine. So the transfer policy is very simple. You have some threshold of load for any definition of load. Load could be utilization of the CPU. It could be the length of jobs in my queue that are waiting to run. Pick any metric, find a threshold. So threshold, let's say 80% utilization. That's my threshold. The load is above that threshold, then you decide to offload job. If the load is below, you say run jobs locally. That's our transfer policy. We'll just define some threshold of load, measure on the local machine, and decide to offload when you are above that threshold. Selection policy says you always prefer to offload a newly arrived job to another machine or one that's already begun execution and has partially executed something. So if you have the choice, you would always take a new job and you would start running it somewhere else, than take an existing one and move it, because taking an existing one and moving it is actually complicated. It requires an OS to support something called process migration, which we haven't looked at yet, but I'll mention it in a couple of slides. That's more complicated. To move a running process is much harder than if I just typed a Python command on my terminal. I just take that command and execute it somewhere else. Much simpler than actually taking a process and moving it. So selection policy says whenever the load goes about threshold T, pick a newly arrived process and move it. Location policy now has to pick a machine to actually run this job that you just chose. So there are many examples here. One simplest one is random. Random just says pick a machine at random, send the job there. If you pick well, then maybe the job, you'll find a machine that actually can receive jobs. Its load is less than T, so it'll run it there. But if you send it to a machine that's also overloaded, it cannot run it, then it will actually send it somewhere else. So your job might have to hop a couple of times because you're randomly choosing based on no knowledge of what is the load on that machine. A better approach is to say, let's just first figure out the load on the machine and then decide which machine to pick to send the job. So you could poll machines sequentially until you find one that has a load under T, or you can probe them in parallel, saying send the load information, you get all of the replies back, you pick the least loaded machine that has load less than T. You can perform either of these two approaches, but in either case, you find a machine that has a load less than T, and the job is going to be sent. All right. So that's our sender initiated policy. Any questions here? So we'll flip and say now we do receiver initiated. So in receiver initiated, when a machine either becomes idle or it has a low load, it goes around looking for work. It goes to other machines saying, do you have a job you want to offload? In the sender initiated, the overloaded machine tried to offload jobs to other machines. In the receiver initiated, a lightly loaded machine goes around looking for jobs to take on. So all of what we said is going to be flipped in this case. So we'll say, what's the transfer policy? A transfer policy is also a load threshold, but it's a low load threshold. If your load goes below a low threshold T, that means you have become lightly loaded, you go looking for work. You become a receiver in the definition of this policy. So a receiver means you are willing to accept jobs to run. So you become a receiver node. What's your selection policy? You still prefer to execute newly arrived jobs, but you can decide to take partially executed job if the OS supports something called process migration, which again I'll get to. Okay? But we still prefer newly arrived jobs just as the previous case. What's your location policy? In this case, the receiver has to go find an overloaded node and ask it to offload some work. Okay? How do you find an overloaded node? Okay? You could randomly contact a node and say, do you have some work to send? Okay? That's a random policy. Okay? You could again probe. You could say, ask some subset of nodes or all the nodes in the network, depending on how large your network is, saying send load information. You get the load information, pick the most heavily loaded node, okay, and then say send one job. Okay? Then you take that job over and you execute. Okay? So those are all approaches you can perform. And you can probe sequentially, you can probe at random, you can probe in parallel and pick the least loaded, okay? Most heavily loaded, and then take a job over. Okay? So this is a receiver initiated policy. Here nodes become receivers when they become idle or lightly loaded, and then they go take on work. Is that clear? Okay. So building on from there, we'll now look at a symmetric policy. In a symmetric policy, you say, why have one or the other? Let's have both. Okay? So now there are two thresholds. Okay? There's a low threshold and a high threshold. Okay? If a node has, a machine has a load that's above the high threshold, it's a sender. It's trying to actively find nodes to offload work. If a node has load below a low threshold, it's a receiver. It's also going to go around actively looking for work. Okay? So you have both of those policies actually operating at the same time. Yes, the senders can actively offload work, or a receiver can go and pick some work from some other node. Okay? So two of these thresholds, you can be a sender, a receiver, or neither. If you're somewhere in between the low and high threshold, you're neither looking to offload work nor looking to take on work. Okay? So you're neither a sender nor a receiver if you're in between. Okay? But if you're above or below the low or high threshold, you're either going to become a sender or a receiver. Okay? If you're a sender or a receiver, you do exactly what we said in the previous two slides. Okay? Senders are going to try to send work. Okay? They're going to go looking for a lightly loaded machine, trying to offload work. Receivers are going to go hunt for work. Okay? They're going to go around looking for a machine to offload work and so on. And both senders and receiver can poll, figure out the load on other machines, ask them to send work or accept work, depending on whether they're sender or receiver. Okay? So now we merge those two approaches into a symmetric policy where you have a distributed scheduler that the OS, depending on the load on that node, can either become a sender trying to send some jobs to some other machine or a receiver accepting jobs from other machine. Is that clear? Okay. Okay, question, that's a good question. Question, how are we going to decide the threshold? Typically, the threshold can be configured by the system administrator. Yes, that depends on how many machines you have and how aggressively you want to send or receive work. Okay, so it's not a, there's no magic number. How do you decide it? You can choose it based on some notion of how heavily loaded a machine must be before you want to send the work over. Okay. No one answer to that question. Okay, so those were abstract policies. I didn't give you much details and so on, but now we look at two systems that actually designed some of these in the early days. Okay? This is where some of these policies came from, and they will see how they specifically implemented some of these approaches. Okay, so we look at two, and then we will generalize from there and look at several others that have adapted them in different ways. So the first one is the V system, which was designed in Stanford. This is all 1980s work, okay, 40 years ago. Okay, this is when some of these approaches were first designed. So that if you read the papers, they're from the 1980s or early 90s at best. Okay? So the V system was one of the early ones. That's a name of an operating system, by the way. That was an early one that designed a distributed scheduler for a network of workstation. Okay? So it had what was called a state chain driven information policy, which means that whenever there was any significant change in load on a machine, that machine would then broadcast its load information to all other nodes. Okay? So basically, you would be receiving broadcasts of any important changes to load on other machines. What that also means is each machine already had a table that told you what the load on other machines was. Okay? So in this case, if you're a sender or a receiver, you don't have to go ask other machines because nodes are already sending their load information to you whenever there is change. Okay? So that's a decision they made, and then we say the M least loaded nodes are receivers. Okay? Others are going to be senders. Okay? And then you implemented a sender initiated policy, which basically used that load information to find the least loaded nodes, okay, which are the M. So M least loaded, and then you pick from one. So essentially, think of, you have a table that's sorted by load. Okay? You pick, let's say M is 5. Okay? You pick the 5 least loaded nodes in the system. Okay? If you become a sender, you are going to pick the top 5 entries, and from that top 5 entries, you are going to pick one at random, and then that's the machine you are going to just send your job to. Is that clear? Okay. Question is, why do you send to M machines? We are not sending to M machines. You are picking one from the least loaded M machines to send to. Okay? So M least load. So you have a table with load information. It's sorted. Pick the top M, which are the least loaded machine. From those M, you pick one at random and you send it to that machine. Okay? So you can say, why did you pick one at random? Why did you not pick the least loaded? Wouldn't that have been better? Why should we do something a little more complicated than why pick the least loaded, send it there? Yes, question. Answer, sorry. You have an answer to the question.
Have a slight delay where everyone goes unloaded, and then everyone tries to send that one node in.
Yeah, so I think if you just pick the least loaded and try to send jobs, there are multiple senders in the network. They might all suddenly offload their jobs to that one node, and it becomes heavily loaded. But if you pick at random, the assumption is that different senders will pick different nodes from that list of M, and then that automatically distributes the load without doing any extra work, right? So this approach, because your M is still a small number, is distributing the load that the senders might send to the receiving nodes. Okay? So that's the reason they picked the randomized policy, because this is actually a good thing. You should not do least loaded, because if many senders send you no jobs to run, then you do not have the benefit of being the least loaded anymore. Okay, so that's the V system. We'll talk about another one. It was the Sprite operating system. This was actually designed more or less at the same time, but this was a project at Berkeley, also in the 80s and the 90s. Okay. So this was very specifically designed for workstations. So some of what I was talking about earlier actually came from design of Sprite operating system. So it assumed users had workstations. Workstations were just powerful PCs at that time. Okay. And the assumption was each workstation had an owner. Okay. That owner, as in not that you bought the machine, but you are the primary user of the machine. Okay. So, and the idea was you should respect the owners of machines. Okay. So what does that mean? So it means that you go to lunch, right? Your machine is idle, it becomes a receiver, okay? And then some nodes offload work, it now becomes heavily loaded. You come back from lunchtime, your machine is heavily loaded, and you cannot do any work because there's so much load that you cannot get your work done. Okay? That's not a desirable situation for a user, because you are letting other users use your machine while you're not using it. But then you come back and you can't use your machine because too many other users send jobs to a machine, then you will not be happy. Then you say, I do not want my machine to be used by others, right? So you want to actually respect the owner. So that's why it means owner is king or queen, depending on however you want to think about it, right? So we want to ensure that users are not inconvenienced, even though they are donating some time on their machines to other users, okay, by accepting their jobs. So we'll see how that is done. Okay? First thing is, let's try to go through our approach and look at how things work. So in this case, okay, so rather than in the V case, remember Stanford V case, the load was broadcast to all of the machines. So each machine had a table which said this is the load on the machine. Okay? In the Sprite case, there was a coordinator, a single machine. Okay, that was a coordinator. All the load information was sent to that central coordinator. Okay? So the coordinator and only the coordinator actually had knowledge about the load on all the machines. Okay. So that is what the information policy, and it was still state change driven. What that meant was whenever the machine had no activity for 30 seconds, okay, no keyboard, no mouse activity for 30 seconds, and the number of active processes is less than the number of processors, which means there's at least one core that's idle, you became a receiver. Okay. So you say, is the user using the machine? How do you check that? You say, is there any mouse activity? Is there any keyboard activity? There's no mouse activity, no keyboard activity for some amount. In this case, they chose 30 seconds, but you can pick any number. And the number of processes on the machine is less than the number of cores. That's our load criteria. You became a receiver. Okay. And then you essentially decide to take on a job, and then that job actually runs on that machine. However, because we want to respect the user, okay, when the user came back, if you are already a receiver and you're running some foreign job, and if the keyboard or mouse activity resumes on that machine, you immediately suspended all remote jobs and gave the machine back to the user. Okay. So jobs are only running on the machine while it's idle and the user is not using their machine. Okay. As soon as the user starts using the machine again, you restore the machine back to the user. The way you do this, you will suspend all jobs that were sent. Okay. And you will actually move those jobs to other machines. Okay. Now you become a sender and you say, here are jobs that are partially executed. They need to run on some other machines to complete. So you'll find some other receivers and send them there. Okay. But to do this, okay, you actually have to now take partially executed processes and then send them to some other machine. That's not trivial. Okay. That requires something called migrating a process, okay, which we'll talk about. Okay. So process migration was first actually invented in the context of the Sprite OS. And this is why they actually came up with it, because they wanted to restore the machine back to the user. But now there's a job that's run for an hour. Maybe it has 10 more minutes of computation to go. So if you kill the job and restart it somewhere else, you have to redo all of that 1 hour of work. Right? So what you are going to do is you are going to suspend the job. You are going to move that job to some other machine that has light load, and you are going to resume that job there. Okay? But that's easier said than done, because this is an actual executing process. Okay? It's not something that you can do trivially. So what you actually have to do process migration is first you suspend the job. Okay? Then you take the memory content, the address space of the job. Okay? You transfer all of that memory to a new machine. Okay? You transfer the registers of that job to another machine. You transfer all of the state of that job to another machine. Okay? You instantiate a new process on that machine that incorporates all of the state, and then you resume the job, which was suspended. You will resume it exactly where it started, and it starts again. Okay? It's a much more complicated process because it involves taking an active process and moving it somewhere else. Even today, you will not find typical operating systems supporting this functionality. Okay? We'll see how to do it in some other context next time, like virtual machine. But process migration, not a straightforward process. But the way you do it is you will suspend, okay, which means that the process will not stop executing. Okay? Now it's frozen. Right? And you'll take all of its memory state, register state, everything, you'll move it somewhere else. And then it appears exactly as it was on machine A, appears on machine B. Okay? You create a new process for that migrated state, and you resume it. Okay? Now, but there are many problems with this approach, okay, because you can say, what if the process was doing I/O? It was actually reading or writing a file on that machine. Now we moved it to some other machine. The file is still on the previous machine, right? So if it starts doing I/O here, that I/O is going to fail. Okay? Now even more complicated is what if that had an active network communication? There was an active socket communication. It was communicating with yet another process. Now we moved that process here. The other process that was communicating to the process doesn't know the process. My process is migrated. It will still start communicating with the process on the previous machine and find that the process disappeared. So all network connections will break. Okay? All file I/O will break. Okay? This is why it's complicated. Okay? Any I/O, network I/O, or network communication, file I/O doesn't work very well with process migration. Okay? But if you didn't have open files, you didn't have active network sockets, you're just doing some compute in memory, okay, you can move that process and start executing it somewhere else, and it works fine. Okay? But that's not a general solution, because typically you don't know that a process might or may not do file I/O and things like that. Okay? So it is much more complicated to actually implement this seamlessly, but they did implement some version of it. It worked fine. Okay? And this is how they said your users get back their machines. As soon as they come back, we just migrate the process. Okay, the question is, do they migrate processes that don't have I/O? So if you limit it to that, then you cannot migrate many processes. So the assumptions, you can make some assumptions. You can assume that if you have a migratable process, it should only do I/O to a network store where the file is not local to machine, it's on some server. So that server is accessible from some other machine, so it can continue to access the file. If you make assumptions of this sort, you can still make it work. But if you're doing local file I/O, of course it doesn't work. The process will just crash when you move it, right? Okay, question is the coordinator doing only these jobs and not other jobs? So the coordinator, what it does is it keeps track of the load. If you need to find a machine to run things on, it knows the load, so it will say run this job there and so on. So it's kind of coordinating where jobs get to run, or if there is a suspended job because the user came back, it will figure out which machine to migrate it to and so on. Okay? Yeah. If you have I/O, this doesn't work. It will just not work because the network connections will break and so on. But we'll see how to solve that problem next time. Okay? But the early versions did not address some of these issues. All right. So moving on, we'll look at 4 or 5 different approaches. There's another one system called Condor, which actually is still in existence today. Okay? So Condor was a system that was designed at the University of Wisconsin. Okay? It also initially started off as, let's try to find idle cycles on a set of machines. Okay? And today you can actually run Condor also. You can, if you and your friends have a set of machines, you can get Condor daemon, run it, and then when you submit jobs, it can actually move things around back and forth. So you can take a set of your machines and your friend's machine and turn it into a small cluster. Okay? And the idea was very similar, but it was designed largely for batch jobs, okay? Not interactive jobs. So if you have large batch jobs, you submit it to Condor. Condor will actually go and figure out, is there an idle machine to run it on? If so, it'll run it there. It actually saw later versions of it started supporting process migrations. Early ones actually did not do it because it also took the ideas from Sprite and say the user returns to their workstation, suspend the job and migrate it. Okay? So this migrate part only works if the OS can help you do process migration. Otherwise, what you do is you suspend a job, terminate it, and restart it. Okay? Which means you throw away all the work it did. You restart it on an idle machine and hope that it will run there before the user comes back. Okay? So this is a system. The reason I'm mentioning this system is it was developed a little bit later after Sprite came about, but it is something that's an active project. Sprite and the system V are long gone. They were designed 40 years ago and the projects ended long ago. But this system is actually still in use. Okay? Many environments use it to implement scheduling on, not on servers, but user machines. Okay? You just harvest user machines, idle cycles, and use that to run all kinds of jobs. Okay, so I'm not going to say much about Condor because most of its ideas were derived from previous systems that I already discussed. But instead, I'm going to talk about other interesting use case here, which is called volunteer computing. So the idea of volunteer computing is, can we try to use idle cycles on PCs at the scale of the internet? Okay? So you have lots of users on the internet. Internet is a very big network, hundreds of millions of users or machines connected, or maybe even billions at any time. So the question is, can we actually look for idle cycles on all of these machines and somehow make use of them? Okay, in other words, can we run really large jobs, okay, on tens of thousands of machines on the internet all at once? Because if you have millions of machines, there may be thousands and thousands of them that are idle at any time. Can we make use of those resources? Okay? That was the idea behind this approach. As the name volunteer computing suggests, okay, you can't just go and run your job on some stranger's machine somewhere on the network. That's not a thing, right? So what you want instead is users to opt in. They want to volunteer their machine, saying, okay, I can let my machine cycles be used for something that is using that to do some computation. Okay? And then you can essentially get jobs whenever your machine becomes idle and then run those jobs. Okay? The way it works is, if you decide you want to volunteer your machine, okay, you have to first download a piece of software from that volunteer computing site, which is usually a special screensaver. Okay? So when your machine becomes idle, the screensaver will activate. Right? You know what a screensaver is, right? So this is not a usual screensaver that's just going to show you some pictures. This screensaver is a special piece of software that's going to connect to a server somewhere and say, machine has become idle, send me a small job. Okay? And the idea is it has to be a small job. Okay? So the machine will send it some small job. It will do some computation, send the result. Okay? The screensaver is still running. It will say, now send me a next piece of the small job. Okay? And it will continue to do this. Okay? And then when the user comes back, the screensaver automatically deactivates. That's how screensaver works. Okay? And then you just stop running that job, because it's a tiny job. You just throw away whatever it is not finished. You don't care about migrating it or anything, because these are small jobs. Right? So you just throw it away, and then the user gets their machine back. That clear? Okay. Now you will say, why would you ever do something like this? Right? Why am I a user trying to donate my cycles? Now it turns out that there are lots of big scientific projects that need cycles to run. Okay? This original project started with the project that run by astronomers. It was called SETI at home. SETI is an acronym for Search for Extraterrestrial Intelligence. Okay? So what they are doing is, they had lots of data from radio telescopes, okay, that are just listening to signals from the sky. Okay? And they're just looking, is there any sign of aliens in that? Is there any actual signal, or is all noise? Right? So your data is, you will just take a small piece of the signal and say, do you find any interesting patterns, or it just looks like random noise? Right? So you're just scanning lots and lots of data to see, is there a pattern there? Is this something interesting in the data, or is noise? And almost always the answer is, there's nothing interesting there. Okay? So you're really wasting a lot of cycle trying to find a needle in a haystack type situation where you don't find anything. Right? Now, because the work is so wasteful, because not finding anything, finding real big GPU clusters or CPU cluster to run this job is not feasible, because you're just burning cycles and getting no useful result at all. So almost always the answer is no, there's nothing useful in the data. Okay? Nobody's found aliens. Right? So what did those astronomers do? Said, let's ask users to donate their cycles on their PCs. Okay? Rather than running this on clusters when you have to pay for it, we'll do it for free. Okay? Users will donate their cycles. We'll just send them a small piece of data. We'll look for something in there and get back an answer. And that's how that project started. Okay? And since then, lots of other projects started, like you were trying to do, let's say, doing some research, trying to find, let's say, a new drug discovery. You're doing cancer research. You're just searching through lots of data sets, trying to find some pattern. Okay? Same kind of problem. Okay? It's really hard to find anything useful. So often the data does not reveal any interesting pattern, but it's a worthy cause. Okay? You might say, okay, I want to contribute some cycles of my PC for helping cancer research. Seems like a good thing to do. So I'm going to go to that site and download the screensaver. And whenever I'm not working, it will do some work in the background. That's fine. Right? So this has become very useful for lots of scientists, because they get lots of users on the internet just donating their PC time for doing something or the other that they find cause with. Okay? That's called volunteer computing. But if you think about it, it's basically doing distributed scheduling at very large scales. Okay? Tens or hundreds or thousands of machines at a time. Okay? And the idea here is, the machine is basically activating a screensaver, it's becoming a receiver, going to some central location. There's lots of data that's been chopped up into small pieces. It gets some small piece. It does some computation on the piece, sends back the result. And then if it still has the screensaver, it'll get the next piece and so on. So you need jobs that are embarrassingly parallel. That can be parallelized and spread across tens of thousands of machines, because you can partition them into small pieces of work, and then spread them up. So this is one evolution of the ideas we talked about, which is, in the previous case, you could think of you as a user were donating your machine time to other users, your friends in your organization. Here, you are doing this at internet scale. Okay, so that is volunteer computing. And that's going to bring us to the third part of the lecture, which is distributed scheduling as it exists today. Which is, we are now going to move from a world of PCs and workstations to a world of servers. And we are going to see how are you going to schedule jobs across large sets of servers in a distributed manner. Okay, so that brings us to cluster scheduling. Okay, so essentially, in today's world, machines are cheap. Right? So not just PCs are cheap, but machines are cheap. So rather than looking for idle PCs, we will just buy a bunch of servers. Okay? And then we'll call them a cluster, and users will submit their jobs to the cluster, and the cluster scheduler will say, I'm going to run that job on this server or some other server. Okay? So that's the job of the scheduler. It's still trying to find a least loaded server or an idle server to run a job. Okay? But this is a dedicated cluster that's just running jobs for a set of users. Okay? Now we'll see two types of applications, and the types of approaches might be slightly different. So one is you're doing this cluster scheduling for interactive applications, which are basically web services. Okay? Those are large web applications. Requests are coming in. You're distributing them across a set of machines. Okay? Here, a job is a single HTTP request. It's not a real job like a big simulation. It's a single request, and you want to serve that request very quickly. Okay? That's one type of cluster scheduling. The other type of scheduling is a batch job. It's the kind of job we are talking about so far. Long-running job takes minutes, hours, days to run. You just want to find some server to run it on, and you run it to optimize for throughput. So in one case, you're optimizing for response times. Web services means you want to respond quickly to users. Okay? Batch application means you want to optimize for throughput. You want to run the maximum number of jobs on the machines and improve their throughput. Okay? So let's look at each of those. Okay? Now, regardless of whether your job is a single HTTP request or a long-running computation, okay, this is the picture we'll keep in mind for our cluster scheduler. Okay? So jobs are going to come in. They'll come into a machine called a dispatcher. Okay? So the dispatcher will have a queue. The jobs will come in and they'll enter the queue. The job of the dispatcher is to basically send each queued request or job to one of the worker nodes. Okay? In this case, the worker nodes are actual machines. So the dispatcher will run an algorithm that'll say, where should I run the next job? And you'll pick one of the workers nodes or servers here. You'll pick one of the servers. It'll send the job there. Job will execute. It'll send back a response. Okay? Notice that the terminology of dispatcher and the worker nodes is the same as what I was talking about last time when we were talking about multi-threaded servers. There's a dispatcher thread and worker threads. Okay? Here, we are not talking about threads anymore. These are actual servers. Kept the same terminology because the dispatcher is waiting for requests and it dispatches the request to another worker node. So it's using the same basic idea, but now you're doing it across servers rather than doing it for a pool of threads. Is that clear? Okay. So now with that picture in mind, let's talk about some details here. We'll first talk about web servers. Okay. And we'll come back to web servers, I think, in maybe a month and a half or so when we get to the web services topic. But this is just about scheduling at this point. We're not really worried about web applications and so on. So requests are coming in. So we have a cluster that's serving this request. Okay? Typically use this cluster for very large websites. Okay? Large websites don't run on a single machine. Okay? Their volume of requests that is coming in is so high that you cannot serve all those requests using a single machine. That's just not going to work. Right? So you have to have a cluster of machines that are collectively serving your requests. Okay, is that clear? So here you have n nodes. Okay, one of them is the dispatcher. Okay, and so the dispatcher is getting web requests and is sending it to one of the web servers that are worker nodes which serve the request, send back a response. Okay, so you essentially have served. So requests are going to arrive at the load balancing queue. You have to now decide, like always, which of the nodes to send that request to. You can use least loaded, round robin, and so on. Okay? And so there are many approaches, and you can pick one of them. Okay? And then there are other approaches that are interesting here, which is you can use what is called session level load balancing or request level load balancing. So what do these things mean? So if you think about how your web application typically, let's say you logged into your favorite shopping site. Okay? You create what's called a user session. Okay? You can go, you can shop around, you can put something in the shopping cart. All of those operations are part of a single user session, right? Until you either find something, you buy it and you close the site, or you do something else. Okay? So if you do session level load balancing, what that means is a user session is mapped to a server, and all requests from that user session are all going to that server. Okay? If you do request level load balancing, you say that each HTTP request, even from the same user session, might go to different servers. Okay? So that's the difference between the two. And typically, you want to do session level load balancing because sessions have state. Like what you put in the shopping cart is the state of your session that has to be preserved at the server. Okay? If you put something into the shopping cart and that shopping cart is saved on one machine, next request goes to some other machine. That machine does not know what's in your shopping cart because that was state of the session which is stored in the memory of the previous machine. Okay? So to keep state information, you want to keep sending requests from that session to the same machine. Okay? This question, yes. Okay, a good question. The question is, aren't the machines all replicas of one another? And will if I put something on in the shopping cart, will not be replicated? That's your question, right? Yeah. So machines are replicas, but replicas just means you replicated the code, right? It's the same code that's running, but the memory is not replicated, right? So if I do something on this machine, doesn't mean that all other machines will suddenly get whatever it's in memory. That's not a thing. So your memory is going to be local to each replica. So this is why state is not replicated. The only way you will replicate that state is you have a database. You don't keep things in memory, but you put the shopping cart into a database. If you put it in a database, the other machine can go and take it from there, recreate the state. But if you keep it in RAM, you're not going to get access to it. Okay? All right. So in any case, session level load balancing is one approach. Request level load balancing is another approach. We'll come back and look at some of this in more detail. Yes, question there. Okay. Question is, are the number of users limited by the number of machine, right? So you will have each machine is serving lots of users at the same time, right? So if in session level load balancing, sessions from some subset of the total users are mapped to that machine. Okay? Some other user sessions are mapped to another machine. It's not saying that each machine is only serving one user. That's not what we are saying. These machines are going to be significantly powerful, so they can serve hundreds or thousands of users at a time. But all requests made by that user to the dispatcher always go to that machine. Okay? So in this case, the dispatcher needs to know that it mapped user I to that node. So any subsequent requests from that IP address have to automatically go there. So all of that information has to be maintained in the dispatcher. Yeah, the user that is why you're using load balancing. So you can look at the load and decide other sessions can be sent to some other machine, right? So that's.
How heavy will be the request?
Yeah, the question is, you don't know how heavy a user request is. These are all web requests, right? So you can predetermine all the types of requests a web server will receive because you build the application. So you can decide based on that what an average request load might be, right? And use those types of profiling techniques to figure that out. There are approaches. I mean, what you're saying is a valid point, but there are approaches to deal with that. Okay? Yes. Okay, the question is, in the multiprocessor case, we said that the queue was centralized queue was a bottleneck. Will that not be a problem here? Okay. So the main difference in the two approaches is in the multiprocessor case, the OS kernel ran on the processor, and the OS kernel tried to pull requests from the queue. Okay. In this case, the scheduler actually runs on the dispatcher node, and it's the one sending jobs. Right? So there is no contention because of that. It's not that the worker is telling, send me a job. The dispatcher is the one that's sending the job. So you don't have that problem in this case. So question is, can you do things in parallel? That depends on the scheduler, but it doesn't really matter. You can do things in parallel too in this case, because there is no contention to deal with, right? You can have multiple threads that are dispatching requests, etc. Okay, so that is interactive. We'll talk about batch jobs. Okay, same problem. Now our jobs are no longer HTTP requests, they're long-running computations. Okay, they're non-interactive jobs. So examples are, you have a machine learning training job. Okay, I have a big data processing job. I have a scientific simulation. They might take minutes, hours, some of them might take days. Okay, and you want to then take these jobs and send them to a machine. Okay. Same idea as before, right? So you will essentially have this queue. The queue is going to be at a dispatcher. The dispatcher decides where to run the jobs and so on. Okay. And there are many flavors of systems that are in use that have been built over the years. There's a common one called Slurm. Okay. That's basically an open source Linux-based distributed scheduler. It's actually an acronym, stands for Simple Linux Utility for Resource Management. Okay. So essentially, it's a batch scheduler. Most of the supercomputing nodes actually use Slurm as their distributed scheduler. There are other commercial ones also, like IBM has LSF, and then there's something called Load Leveler and so on. Those do similar things. But by and large, what they do is they allow you to submit jobs to a cluster. The scheduler decides which jobs to run it on. But there are lots of interesting nuances here. Instead of a single queue in that dispatcher that I showed you, that this dispatcher, in batch jobs, you can have multiple queues. You can say this is a large cluster. It's used by multiple research group. Okay? Let's give each group its own queue. Okay? Let's give each group a quota so that one group doesn't go and hog all the resources on the entire cluster. Right? So you can have group-specific queues. You can have resource allocations for those queues. Okay? You can specify time limits. You can have a long job queue and a short job queue. If your job is short, you submit it to the short job queue, it runs faster. Okay? Long job queues, maybe because you want to give priority to short jobs, long job queues take longer to run. So if you have a longer job, you put it in a different queue. So there are more sophisticated schedulers here, more than one queue. You can submit jobs to specific queues, and then the scheduler has to make sure all of the queues are serviced based on some policy. Okay? So the policies here get a lot more complicated than let's just send to the least loaded or something like that. Right? Because you are going to have to decide how to enforce the quota, how do you prioritize one type of job over the other, short jobs or long jobs, or if some group essentially gets a bigger quota, how do you make sure those jobs are actually given more servers in the cluster than the ones that have less quota. All of this has to be enforced by the scheduler in this case. Okay? And we'll come back to some of this again at a later time. Any questions on this? All right, so we will actually end it here. We will talk about Mesos and Borg next time. Okay? And we'll also switch to a new topic.